Hey, it's still Cooper, and this is still machine learning. Today we're going to be doing convolutions, which is a nice little trick in machine learning that is going to be very nice for us to know. So, let's do a little bit of recap. We're also going to change our notation a little bit to make my life a little bit easier. So, we have our perceptron, and of course we have our neural network, which is a combination of the perceptron idea into multiple layers. And what we're going to do is we're going to change this notation because we have these fully connected layers and there's a lot of arrows going on, but we basically will always use these fully connected layers. So what we're going to do is we're going to use this notation instead. In common practice, and if we are doing a more explicit model, we'll want to say how large the input and output of each of these are, but for our practice, we will just have these fully connected layers. You'll see this notation, this sort of notation, at least in papers, because it's a lot easier to describe the network in this sort of format instead of like this. Now, last time we also did make a change to our model, and we'll see how it reflects in our new notation. So we went from this just fully connected, fully connected, fully connected, to now having these functions in between, which are our non-linearities. So this is what our network looks like now. And this will actually look pretty similar to networks that you'll see in papers, but there will be some differences. At the end, we'll actually see one that will look like a proper paper. All right. So let's switch it up. Let's do something very different. Here is a picture of a frog, as you can tell. And what this frog is it is an item from a new data set, and that data set is SAFAR 10. They're images that are 32 by 32 by 3. We have color now. And it has 10 possible classes, one of which I would wager to bet is frog. So what we're going to do is we want to, instead of just using these pixels, because we're getting a little bit large now. I mean, we started with our 28 by 28 images of digits, which is fairly small, and now we're looking at 32 by 32 by 3, which is not too much bigger, but is reasonably bigger. So we want to use features instead of just the pixels. And we want this for a couple of reasons. We want it so that we can, shrink down the size, hypothetically, but we also want this because there might be more information in features of this object instead of just the pixel values. For example, if we can tell that it has like a circle with a dot in the center of it, and we can tell it has 2 of them, then it might be a lot easier for us to tell that this is a frog rather than just looking at these pixels and saying, oh yeah, this is the relationship between these pixels. This is sort of the idea of convolution, which we'll get into now. So yeah, we can do that. Otherwise, there wouldn't be much of a presentation, would there? So this is convolution in as best terms as I can give you. So we'll start with an image. I put 1s and 0s here, but it can just be float values. 1s and 0s are just easy to write. And what we do when we have convolution is we are going to define a kernel. So the kernel is going to be some matrix. It can be of any size. It has to be actually smaller than the image, but any size. And what we're going to do is we are going to overlay the kernel onto the image. We're not going to literally overlay it, but what we're going to do is we are going to calculate the element-wise multiplication of this matrix and this segment of this matrix. So if we want to do that out, we can see that if we take each of these and we multiply it by its respective element in the kernel, we'll get this, which will end up being 4. So what we're going to do is we're going to find our output from this, which is actually going to be smaller, you might notice. And this first placement of our kernel will correspond to the first element of our output. So this value 4 that we calculated from here will go into that spot in our output. So you'll see we put 4 there. That's nice. So what we're going to do with our kernel is, of course, that's our first place to put it, but where's the second place we put it? What we're going to do is we're going to take our kernel and we're going to move it across the image. We're going to put it on every different spot that we can put it, every different segment. We're going to move left to right and then from up top to down. So we're going to go left like there, and then we're going to go down to this spot and keep going left to right. So the next spot on this output would be right here, would be overlaying our kernel right here. So you can see the corresponding values. And I'm going to ask you what this value would actually be. So I want you to, again, pause it, take the second. It's very simple math, but it's worth just, seeing so you can sort of get an intuition for like what the values of a kernel of this output will end up looking like. So take a second. That's enough of a second, and you would get the value 3 from it. Sorry to spoil it if you didn't pause in time. All right, let's get a visualization though of what this process this process looks like. And I actually have this exact example, although the colors are swapped on here. And this is a GIF, so it will go through, and you can see that it will go through each of these, it'll do the multiplications, and these are the values that are coming out of it. Now, there's one key intuition that I want you to get away from this, and we can see it here. So the kernel has these values inside of it, and if we look at this particular example, we see that there are higher values along this cross, and there are low values everywhere else. What this means is that when we put this over this image, remember this is an image, where there are aspects that look like a cross, so if we find any place that looks like it has a cross on it, the corresponding output value will be very high. And where we have a place that doesn't have a cross or has the opposite of one, it would be very low. So this sort of corresponds to a feature, as we'll end up seeing. This is like a filter that we put over the object, and we'll see where that feature is most prominent, and that will correspond in our output. So this is sort of an intuition to get for it. It might not be obvious now, but hopefully by the end of this lecture, it'll be a little bit more obvious. All right. So let's see. We have the kernel here right now, and what we're going to do is we are going to move it over, right, as we said before, but we're moving it over by 1, and that is not actually the only distance that we can move it over by. In fact, the distance that it moves over is called the stride, and this will actually become a new hyperparameter for us to have in our neural network. So if we have a convolutional layer, we need to keep track of the stride. And in fact, we also have to keep track of the height and the width of our kernel, and it's a lot of extra hyperparameters. So we need to choose how big this is going to be and how far over it's going to move. And in fact, you could probably get some intuition from this now, but that's actually going to change how big our output is too. Now for the kernel, we haven't really mentioned this, but each of these values inside the kernel, every single one of these, is actually going to be a new parameter, and we're going to update it. So we're going to have this be a layer, we're going to have a convolutional layer, as we call it, where we will perform this operation, and we can still backpropagate through it to update each of these. So that's a nice new property that we have, and we'll actually end up changing what this filter is. So let's see what a convolutional neural network looks like, as we call it. That is when we use convolution in our neural network, basically. So what we're going to have is, this is our current neural network, right? Very simple. We do our nonlinearities and we get our output. What we're going to do is we're going to add a convolution onto the front of it. So we want to do the convolutions on the front. That is the common practice, mostly because of AlexNet. I mean, you could do it throughout the network, but it is not seen as good empirical results. So in general, we put it in the front. So not only can we just have a convolutional layer in the front, but we could actually have multiple convolutional layers. We have a convolutional layer that goes into a convolutional layer that goes into our classifier. So we can have pretty complex networks like this, and we can have as many convolutions as we'd like, although there is reason to only have so many. So what we see is that these convolutions will reduce the dimensions of the data, or will reduce the size of the data, of individual pieces of data. They don't necessarily do that, but we can do that, so that the classifier here will train faster and better. Really, we want to harp on that second part. In general, if we have large convolutional layers, we'll see what that means later. It won't necessarily be faster. In fact, it could be a little bit slower, but we will see that it will train better in general on vision problems in particular. So keep that in mind. That's a really nice thing for us. All right, so let's see what those filters, we saw that one kind of looked like an X, but we can do a little bit of visualization on them to see what they might look like, or what they do look like, after we do a full set of training. So here we have a visualization. So these right here are the first layer filters of this is like a 3 convolutional layers. This is the first layer. These are what the filters look like. Then we have the second layer, and these are what the filters look like, and then the third layer, and these are what the filters look like. So if we look at the first one again, we see that they're very simple things. They're like stripes, there's little colors, there's color blobs, and these are the sorts of things we're looking through across the image. So if we're looking for these stripes, we might look for like the undercarriage of this car, maybe the grill. So we look for very simple things with these first filters. Once we jump to the second layer filters, they get a bit more abstract. We can't really exactly tell what they're looking for because they're looking through this first layer too, so they're a bit more complicated. And of course we can look here and they start looking nonsensical. I mean, these actually look a lot like wheels. So this is probably trained on some car data set, actually, we could presume, but we can't quite make out exactly what they are. So really, as we do multiple layers of convolution, the features that we get will end up being more and more abstract to the point of being not readable what they're doing anymore. And then those features, though, although being very hard for us to, they are very good for our classifier to actually train on. So we like having these abstract features, and they do perform very well in practice. So sort of soak this in. This is a weird concept to get right here, but if you get it, then convolutions make a whole lot more sense, and you start seeing data a little bit differently too, or at least image data. It's an interesting thing. All right. So let's talk a little bit more about the details of convolution. As I mentioned briefly earlier, the hyperparameters can affect the size of our output when we're doing a convolution. So let's imagine we have some 32 by 32 input, and we have some 4 by 4 kernel. Let's say that, so our stride again is how far we move it over, and let's say that our stride is 1. I'm going to take you a second to try to figure out what the output size would be there. So just try doing it out by hand. This is going to be an important thing for you to know how to do. You're going to have to do it by hand to design your neural networks, as long as you use convolutional layers, which you probably will. So do get some hold of this. We'll give you some formulas and stuff in a minute, but just try doing it by hand for now. All right, so what we end up getting is that it'll be 29 by 29. You can try to convince yourself of this, try to figure out why that would be. I mean, 32, 4, maybe you subtract them or something. So, we'll get 29 by 29. But what will happen if we have stride 2? Once again, I'm going to say try to take a little bit of a moment and see what you can figure out here. See if you can figure out what it is. And I'll get back to you in a second. All right, so hopefully you got it. It will be 15 by 15. So you can try to convince yourself of both of these, but I'm going to give you a formula now to help you with that. So what we'll see is that we will actually have that the output height will be the input height, so the height here, minus the convolution height, divided by the stride height. And this is indicating, and if you picked up on that, good job, that the stride can be different in the two directions. So it could be more in width than it is height. That's totally feasible, but generally it will be the same. So you can, in general it will be the same, but it won't necessarily be. So keep that in mind. And then we add 1. You can try to figure out why if you'd like, but you can do it geometrically, and it's a pretty satisfying reason. All right, and we can also do the width. It's exactly the same, just width minus width divided by stride width plus 1. So this is our formula for now. It will actually change in a moment as to how we get our dimensions of our output. So keep that in mind. It'd be good to write this down, even though I just said we're going to change them. This is still important, and for the most part, you'll probably do it like this. All right, so let's talk about a different stride. Let's talk about stride 5. And once again, try doing it out by hand a little bit. I'm not going to give too much time now, but I'll start doing it. So what we see, we can use our formula right here. Okay, let's plug in the values, easy enough. 32 minus 4 divided by 5 plus 1. Okay, that gives us 28 over 5 plus 1, which gives us 6.6. And that's not really something we've talked about. We got a fraction here. And the outcome is we actually can't do that. That doesn't make any sense. At some point, we'll have our convolutional filter sitting over the edge here, and we will be multiplying by nothing. And that doesn't actually work. We need to have something to multiply by. And we're going to come up with an answer, and it will be basically as close to multiplying by nothing as possible. And we call this padding. So what we're going to do is we're going to take our regular 32 by 32 image, and we're going to add a layer of padding around it. So this padding is going to be made up entirely of zeros. So we're just going to have our normal input with all of its float values, and then just a ring of zeros all the way around it. So now it will be 34 by 34, and this is a padding of 1. So it's 1 0 all the way around. Right? Do note that it is changing the dimensions by 2 in each direction because we're padding by 1 all the way around. We don't pad by a portion of it, we pad all the way around. So now let's try actually doing this with our 4x4 convolution and stride 5. Now if we try it, we can do out the math, and we see that we get actually a new formula here. So we do our input height plus 2 times padding. You see it's a very similar formula. We're just adding our padding values to each of the dimensions. And then we can do the formula like usual. And if we plug it in, we see that now we have a reasonable height for our output. So we use padding if we want to have control over our output size, or if we have particular kernel sizes that we'll want to use with some particular stride. Padding does lose a little bit of information. I mean, on these edge ones, we are multiplying by 0, but in general, this is totally fine to do. We just end up with some slightly less useful parts of our output. All right. So what about color? So we talked about like these 2 dimensions. That's all well and good. But now we have our input, and like we saw with Safar, we have color images. So it's not just 32 by 32, it's 32 by 32 by 3. So what we say is that we have 3 channels. So this is the same as having an input that is 32 by 32 by 3. It's the same as having a 3-dimensional input. But for the sake of convolutions, we're going to call these channels. All right? So when we have 3 channels in our input and we want to do a convolution on it, the convolution will itself need to have 3 channels. So it will essentially be a 3-dimensional object. And of course, we can still do the normal way we do convolutions. We'll just have it across a 3rd dimension. All right? So it won't need to move in that 3rd dimension. They have the same dimensions there. It'll just move across like normal. So one interesting thing about this is that if we do this operation, right, we'll end up with some output. This is saying stride 1, so we get 29 by 29. And the question becomes, how many channels does this have? What are its actual dimensions? We have 29 by 29, but by what? Take a second to think about it. I guess don't think about it. It's 1 channel. So in fact, what we see is that when we multiply these, so we're multiplying across all 3 of these dimensions. When we do our convolution, we're doing our dot product like that. We will only end up with a single value. So we actually get rid of all of these channels, and we just end up with a single channel, a single value for this area of the input. So we will actually destroy our channel by doing that. Now, that does not say that we will always end up with 1 channel when we do our convolutions. In fact, we can do something kind of cool. We can, instead of having a single convolutional filter, have many convolutional filters. So now we have 3 channels on each of these. Each of these are still 4 by 4 by 3, but we will have 10 filters. And you can try to guess what happens when we do this operation now. This is essentially adding a new dimension onto our convolutions, which are now essentially a 4 by 4 by 3 by 10. So don't be too scared of the fact that we're adding a lot of dimensions. You can just think of it as having a bunch of different filters and having them all be color filters. All right. But what we end up seeing happen is that when we go to take the output, it is still a 29 by 29, but now it has 10 channels. So it's a 29 by 29 by 10. So we have 1 of these channels for each of these filters. All right. So this, as you might have seen, as you might be able to see very quickly, has actually increased the size of our data. So now we have a bigger data. But what is interesting is that we have a bunch of different filters, and each of these different filters can see something different about our input, and we actually get very good behavior out of this. So we actually do want to do this sort of thing. Just as a quick aside, to show you what would happen if we have multiple convolutions with these channels and all of this weird behavior. Say we have this, which is the example from before. We have the 3 channels, so we actually use the notation that's in channels and out channels. When we do PyTorch, you'll actually see that written out explicitly. And say we want to do this, and then we want to have it go to another convolutional layer that has 5 filters. We'll have that convolution will have 10 input channels and 5 output channels. That'll be 5 filters. You can count them. It's not 5, but I'm going to say it's 5. So we'll end up with 5 filters. And then we can do this again. We can do this as many times as we want, and we'll just be changing the dimensions of them as we go. So we can just do this as much as we want, and we can basically end up, after doing convolution, with data of whatever dimensions we want for the most part. All right, so that's convolution. Hope you got all of that. Next time, and in the next video, we're going to be going through a coding example of actually implementing convolutions in PyTorch. So I hope to see you there, and that will be a little bit more hands-on.